Hi everyone and welcome to my talk on our article titled Procedural Bridges and Pillars Support Generation, where we will be talking about support generation for 3D printing. 3D printing allows us to create physical shapes from a digital model through various techniques such as fused filament fabrication or stereolithography, among others. These fabrication methods impact what can be printed. In particular, most methods operate layer by layer. This becomes a problem for objects containing steep overhangs and local minima. These objects rely on support structures to be printed. Trying to fabricate them without supports leads to this kind of result. To avoid this problem, we can use support structures. As you can see, there is a large overhang in these objects that needs to be supported. There are many support generation techniques balancing reliability, sturdiness, printing time, material cost, and plenty of other factors. Our algorithm improves the generation of the bridges and pillars supports introduced by Dumas and colleagues in 2014. These support structures are shown to print reliably, be material efficient and stable in their article. Unfortunately, their algorithm scales steeply with the number of points to support, which I will refer to as anchors in the rest of the presentation. This is a problem for objects with many overhanging features. Additionally, the public implementation of the method does not avoid intersections between the object and the support. This makes support removal harder and leaves scars on the printed object. You can see on the right, circled in red, some zones where the supports generated by this method intersect the figurine. Our goal is to have the best of both worlds and generate the same kind of structures while efficiently avoiding collisions with the object. Our algorithm is inspired by example-based model synthesis. Algorithms such as model synthesis and later wave function collapse procedurally generate content similar to a provided example by extracting information from it. These are essentially tile-based constraint satisfaction solvers, where the constraints are adjacency rules on the tiles. On the left, you can see the result of model synthesis applied to a small castle tile set, shown on the top right, generating a large 3D castle-like structure. On the right, you can see the wave function collapse algorithm taking small images as an input and recreating similar patterns at a larger scale. These algorithms might encounter contradictions at runtime. This happens when no tile is allowed in some cell, which has to be addressed by backtracking or by restarting from scratch. Mirel realized that the larger the domain is, the more likely it is that the algorithm will run into a contradiction. Our contribution is a support generation algorithm inspired by model synthesis that creates a bridges and pillars support structure for any given voxel object. The object along with the supports can then be sliced and printed. Collision avoidance is baked into the method and incurs no extra cost. Finally, generation does not run into contradictions and always succeeds first try without trial and error. In order to explain the synthesis process, let us switch to 2D for a moment and introduce a simplified set of labels, or tiles. These can be used to generate a subset of our support structures. When providing a voxelized input object to the algorithm, each voxel can have different labels, shown here on the left. It can be either part of the object, an anchor, meaning a point needing support, it can be part of the ground, or finally just empty. A voxel in the generated support structures can be, as shown on the right, a part of a horizontal bar, a part of a vertical pillar, a junction between a bar and a pillar, or just empty. The empty label appears on both sides and can be provided as an input, but also can be generated by the algorithm. In reality, we have many more support labels than these. For example, we also have labels for different kinds of junctions between pillars and bars. There are also additional labels to account for the extra third dimension. Adding more labels allows us to have a finer control over the generated structures, but increases the complexity of the system and makes the design process more difficult. Having a set of labels, we now need to know how they can be placed with respect to each other. This information is provided by a set of adjacency constraints. Given any label, here the bar label, we store the labels it can be adjacent to in every direction. A bar label can be adjacent to another bar or to a junction to the left and right, but it can only be adjacent to an empty label from above and below. These constraints can be defined similarly for the other labels. Our method is example-based, meaning that the adjacency constraints are extracted from an example model. This example model should be seen as a compact representation of all structures that can be synthesized by the algorithm. The constraints are extracted by looking at every pair of labels in every direction in the example and marking them as allowed. Let us find what labels are allowed next to a pillar label from this example on the left. Each time I add a new label to the allowed set, I will highlight the corresponding pair on the example model. Let's first look at the left and right directions. We see in the example model that the bar label is adjacent to a pillar label on its right. We can then add this combination to the set of adjacency rules for the pillar label. This is also true on the left. Finally, a pillar can also be adjacent to an empty label on both the left and right. As for above and below, pillars can be adjacent to pillars vertically. They can also be right below anchors and right above junctions. And finally, pillars can connect to the ground. This gives us every label a pillar can be adjacent to in every direction. Constraints for other labels are extracted in the same way. Now we have all basic elements necessary to properly explain the synthesis algorithm. The algorithm takes a voxelized object as an input, shown here on the left, mainly consisting of object labels and anchor labels, marking the points to be supported. The rest of voxels are either empty or ground. Using the adjacency constraints extracted from the example model, we synthesize a support structure that properly supports the object, while avoiding collisions with it. A possible support structure that could be generated by this synthesis process with this set of adjacency constraints is shown here on the right. Let us focus on the synthesis process now. The synthesis process is pretty simple. At first, the model is initialized with the provided input. All empty voxels are marked as unassigned and stored into a set, shown here as a question mark. The algorithm stops when all voxels have been given a label. In each iteration, an unassigned voxel is chosen from this set. Let us take, for example, the voxel shown here in green. Then a label is chosen from the set of allowed labels for that voxel, and is then assigned to the voxel. This assignment restricts the allowed labels in the rest of the domain. In the neighboring voxel, a label that was previously possible might now be forbidden after the assignment. This information needs to be propagated to the rest of the domain, removing allowed labels when necessary. For example, this voxel just above could contain any label before the assignment. But since a junction always needs a pillar on top of it due to the adjacency rules, this voxel can only be a pillar after constraint propagation. Synthesis terminates when all voxels have been given a label. A possible output of the process is shown on the right. This method offers a great deal of flexibility in crafting a custom example model, and also in the way we choose the next unassigned voxel and its label. By tweaking these elements, we can completely change the type of structures that we generate, encourage certain properties in the final structure, or change the behavior of the algorithm itself. Our contribution consists in an algorithm that hinges on this synthesis process, where we tailor the labels, constraint set, voxel and label heuristics, to generate proper supports for 3D printing. We use voxel and label choice to avoid contradictions during synthesis with our set of constraints. For voxel choice, we operate slice by slice from top to bottom. For each slice, we first compute the seed voxel shown in red. These are the voxels that continue the structure of the layer above. Then within a slice, we choose voxels by increasing distance to the seeds. First, we choose the labels given to the seeds, then to their neighbors, and so on until the whole slice has been assigned to. Once a voxel is chosen, we give it a label based on priority rules. A crucial rule is that the empty label has the highest priority, preventing uncontrollable growth and encouraging sparser structures. Our synthesis algorithm operates in two synthesis phases. Here, our input model consists of 3 slabs needing support and an obstacle on the ground that the supports will have to avoid. First, we take the input model and synthesize a solution supporting every anchor with a restricted set of structures. You can see here how the algorithm generates support structures that avoid the obstacle for the middle slab, while it generates simple vertical pillars for the outer slabs instead. This first solution is very inefficient and can be improved. This is the role of the second synthesis step, which takes this first result and optimizes it by relaxing the set of constraints, allowing the creation of bridges, here shown in red, between pillars. This makes the structure more robust and material efficient. A core aspect of our contribution is the fact that object avoidance is encoded in the adjacency constraints. An object voxel cannot be adjacent to a support voxel in the resulting structure. Our set of constraints for the first phase allows the following structures specifically designed to avoid the object. These are, from left to right, a single pillar, a table consisting of a bar resting atop two pillars, and two tables stacked on top of each other. Using a very restrictive set of constraints allows us to tell which of these can be used to support an anchor, just by looking at the allowed labels of the voxel below it. The first phase uses this information to generate the simplest structure to support each anchor. These structures are simple and separate, meaning that the output will contain a lot of redundancy and disconnected structures. The second synthesis phase makes all of these into a coherent, better support structure. Finally, if none of these structures are possible, we exceptionally create a contact point allowing a pillar to stand on an object. This happens rarely in practice. In fact, as you can see on the right, I had to try very hard for the algorithm to generate this kind of structure. Here are some objects printed without supports. Note that the stringing only happens between the supports and does not touch the object itself. It results from slicer optimizations. The object on the left has 1 million voxels and 341 anchors. The supports were generated in 9 seconds without any new contact points. The object on the right has 200,000 voxels and 37 anchors, and the supports were generated in 1 second, creating 2 additional contact points. Also note how on the left, the supports go through the small hole to support the arch without intersecting the object. These examples show how our algorithm performs for cramped geometries, where there is little to no room for supports. The example on the left has 300,000 voxels and 347 anchors, and the supports were generated in 2 seconds without any new contact point. As for the knot on the right, with 199 anchors, the algorithm created 33 new contact points, which is pretty high for our standards. This is due to the threefold rotational symmetry of the shape, which clashes with the axis-aligned generation method. Here we printed the supports in a different color. We can see after removal that the area of contact between the object and the supports is pretty small. The object has 1 million voxels and 235 anchors, and the supports were generated in 9 seconds, creating a single new contact point. We also made a few time lapses showing the models and the support being printed. We first printed a Minotaur figurine here. Then we decided to get a little creative and print it upside down. And then finally we decided to get even more creative and just print a bunch of Perchy models floating in the air. Our method has some limitations. Compared to the previous algorithm for generating these type of supports, ours tend to generate more redundant structures and thus may consume more material on average. You can see on the left that there are many horizontal bridges in the support structure. This also allows us to print them thinner, though, making it hard to compare ourselves to the previous method in terms of material efficiency. Also, the support quality greatly depends on the object orientation, since we work on a 3D voxel grid. Most of the time this is not a problem since the best orientation is usually easy to find. For the example on the right, it is clear that the supports will be better if the object is axis aligned. In conclusion, we present a novel algorithm for bridges and pillars support generation. It avoids contact with the object when possible without incurring any extra costs. In practice, it always finds a solution if there is one. We tested this on a 1000 object benchmark without any failure case. Finally, the worst case complexity depends only on the voxel grid size, scaling with the square of the number of voxels. Thank you very much for your attention.